Hi, everyone. I'm Rachel. I'm the president of Codeducation. Today is our introduction to deep learning and Python workshop.
Hi, guys. I am Bailey. I am the vice president of the club.
Hey, I'm AJ. I'm the secretary of the club.
Hi, I'm Kathleen. I'm the outreach coordinator.
All right. Welcome to Deep Learning Introduction. I'm Aditya. I'm a PhD student in computer science here. This presentation is, I have tried to keep it as little, math as possible, because deep learning normally involves a lot of complicated, calculus, like matrix calculus and whatnot. But this is more of a very watered down, as much math free as I could, presentation. It's just to make you guys understand what happens behind the scenes. So before we go, tell me something. Can anyone here tell me what these numbers are? Yeah.
5, 6, 9, 6, 7.
Okay. So this is pretty easy. We can all know that these are 5, 6, 9. But the question is, how did you guys recognize them? Think about it. Those two 5s, they look pretty different, right? The two 6s, very different from each other. But how did you manage to recognize how, both of them as 6? And how did you manage to differentiate between 1, 5 and 1, and the 6? The idea is you were looking for patterns. Think about it. Whenever it comes to 5, one pattern you can think of is there's a straight line on the top, a slanted line on the, or a line downwards, and then there's a curve. Those are called patterns. That's what you want to see when you're looking for a 5. The reason you said that that was a 7 and not a 1 is because you saw that there was a straight line like this, and then a downward diagonal line. These things, these are called patterns, or rather features, as we call it, identify certain things. For example, the reason you can say that's a 6 is because it has a curved sort of line, and at the end of that curved line, there is a little, a little round thing. That's how you know that's a 6. If, on the other hand, that round thing was up on top, it would have been a 9, right? That's pretty much the fundamental thing about any kind of learning, be it artificial intelligence, machine learning, deep learning, be it even human learning. Patterns. Without pattern, there's nothing to learn. For example, you can try, but you will never get better in learning what the next roll of a dice will be. You can only detect that, okay, it's between 1 and 6, but you won't be able to figure out what that next roll is going to be, because again, it's random. Anything that is random cannot be learned. What we need, how we learn, is by finding patterns. Now, how do we find patterns? Well, we repeat something. You remember that phrase, practice makes perfect? That's kind of true, because the more you practice, the more you see detailed understanding, you get a detailed understanding of what the pattern is that you're trying to learn. For example, before we try to make computers learn, let's see how humans learn themselves. First thing is, we know how good or bad we did at something, or how good or bad something is. For example, think about it. When you're doing karaoke, right? You have there is something inside your mind, like a metric, that tells you, am I singing in tune, or am I, going way off key? How am I, do I have to look at the lyrics, and am I just reading off the lyrics of the screen, or am I actually, remembering how each word is supposed to be pronounced and whatnot? Those are metrics that determine how good you're doing at something. We need one of those first. The second thing is, we need to check our performance periodically on that metric. For example, let's say the first time you tried to, sing one of your favorite songs, right? Probably what happened was you were pretty much off key. You sang so good that some people went deaf, probably. You probably didn't remember anything other than the chorus part. And overall, it was probably a very embarrassing moment for you. So what you did was, you then tried to see what you did wrong, tried to, again, have a go at it. Tried to, look up the lyrics, try to memorize part of the song, like, first part of the song or second part of the song, the one that you missed completely. Try to get a little bit, try to get an understanding of how to modulate your voice so that you can sing properly. Try it again then. This time you were still terrible. You pretty much, didn't remember one half of the song, but hey, you did better. Your voice wasn't too off key. You remember the first part. Again, you did the same thing. You looked at the lyrics, now at the part that you missed, like the last part, did the same thing over and over and over and over again. Finally, you master it so well that your cover becomes better than probably the original song, according to some people. This is deep learning. What we do is we basically make the computer a task and make it like it basically repeat. Like we basically make it repeated, what we call as repeated learning, basically. For example, let's say you have this neural network. I know we haven't talked about it, but think about it as a tiny brain, all right? And you want this tiny brain to, for example, identify the, handwritten digits. For example, this is a 0, that's a 2, that's a 1. These are all, written by someone hand. This is actually from a data set. If you ever want to get into deep learning, this is probably the first data set you will use. It's pretty much the hello world of deep learning called the MNIST data set, handwritten digits. So what you do is you basically give this thing called a training data, which is sort of like, imagine a real life example would be, in kindergarten, they have this large books that has like, colorful zeros and ones written for, the kindergartners to learn about numbers. It's pretty much the same thing. Training data is pretty much the same thing. This is meant to be used to make the, little brain recognize zeros, ones, twos, and so on. So what we do is we first tell our brain that, hey, can you identify these? The brain probably does not so well. In this case, as we can see, it identifies a 2 as a 7. Then we have this thing called a loss function. An error or a loss function is sort of like a metric. That, again, remember that one metric I said that we always have something that tells us how badly or good we are doing something? That's the error function. The higher that function is, the worse our brain is doing. In this case, for example, the error function will tell us that the brain is doing good, like the neural network is doing good, but it still isn't, like it could go way better. It's saying that this 2 is a 7, probably making other sorts of mistakes. This is then taken to something called the optimizer. An optimizer is like a teacher or the teacher of this neural network. What this optimizer does is it takes the metric, it sees how bad or good you did and says, okay, so if you manage to do this, if you manage to fine tune this, like if I manage to fine tune this part of the brain, I can get a better result. For example, in this case, the optimizer might be like, okay, this neural network, if I fine tune it like this way, I might be able to make it recognize that 2 as a 2, as opposed to misclassifying it as a 7. This entire thing is called a training loop. This entire thing happens on repeat. It goes on like this, You'll always you have for example, we do it for 100, 200, 1,000 times at times, especially for harder problems. The more it sees the, same things, it sees these, numbers, the more it realizes, what am I supposed to be looking for? Now, in that sense, let's go and start with the coding a little bit. So for today, what we're going to do is we're going to use something called Keras or TensorFlow. Have any one of you guys ever heard of this? Good. So for anyone else, Keras is sort of a, what is it? It's one of the best deep learning libraries in Python. There is another one, it's called Pytorch. Pytorch is more advanced. It's like, if you want to really, work with deep learning, make your own neural network with fancy stuff, then you can use, Pytorch. But Keras is more like plug and play. which is like a very good, it's a very good tool to introduce deep learning to people. And we're going to try to use that in this, we're going to try to make a model in Keras to identify handwritten digits, for example. So Numpy, how many of you guys don't know Numpy here? Okay, Numpy is basically a sort of tool that we use to convert lists in Python into, mathematical arrays. So it basically helps, instead of trying to do list comprehensions, Numpy basically helps easily in doing things like matrix multiplication, tensor multiplication, statistic stuff, like, for example, let's say two arrays, you have two matrices, let's say, and you want to find the distance between the two matrices. Numpy does it fast and it does it efficiently. It's basically a way of changing the lists to pretty much, mathematical arrays. Other than that, Matplotlib is a plotting function. It's used to plot graphs, show images, and stuff like that. So, for example, Keras has its own bunch of data sets. Normally in keras.datasets, if you go here, you will get into this particular place, which is a bunch of data sets that we can use, like toy data sets rather. These are really good, and even till this day, when it comes to deep learning research, I have done it, a lot of other people have done it. These are some of the best data sets that you can do your research on. Like, you'll see any deep learning publication, you'll see them using either MNIST, which is that handwritten digits data set that I showed you, or CFAR100, CFAR10. These are very famous data sets. These two are object recognition. Fashion MNIST is basically, fashion recognition, I would say, differentiating between a jeans and a skirt and stuff like that. But right now, we are going to use MNIST, and load data basically, is a method that pretty much loads, the data into these two things. So one thing is, there is a training set. The training set is meant to be the one that, your neural network sees and trains on or learns the patterns through. And then there's a test set. The test set is pretty much like exam, an unknown, set. So it's sort of like this. Let's say this training data. Remember the kindergarten example where you had a kindergarten, those big zeros, ones, the big colorful, digits that are used to learn, make the kids learn? That's the training data. The test data is like you saying someone else writing a 0, 1, or 2. You want to do really good on both, but most importantly, you want to do good on this one, because this is real life. So what we do is, first, let's say this is how this training data would look like. So I'm just printing out here the training data. Let's say let's print out the 2. All right. Let's actually first run this. Takes time because Keras is a bit of a, So as you can see here, you see these numbers. You see how it looks like a 4, right? Because it is a 4. These numbers are basically pixel values. So you know how pixels have 0 means, dark, and 255 means white or light. These are those values. As you can see, 245, 254, this means high, almost white. The reason this is this only looks like black and white is because it's it's not RGB, it's just one channel. That's why it's pretty much, dark. Sorry, black and white. We can do, now, we come back to one thing before I move any further. There's also one other thing, which is, we've been talking about neural networks a lot, right? But what exactly is a neural network? What is this neuron thing? So you guys know how our brain works, right? We have something, our brain is made up of a bunch of neurons, right? In computers, we kind of try to do the same thing. For us, a neuron pretty much is something that holds a number. That's it, all right? What this number means, we'll come to that. Normally what happens is, because of certain reasons, we want this neuron to have a number between 0 and 1. You can go a little bit above or below that, but we normally try to keep it between those two values because otherwise it creates a lot of problems. A neuron, the higher the neuron's number, the more activated it is, the more it is what we can consider as turned on. So again, the main question comes out as, what is that number supposed to signify, right? That number signifies the neuron detecting a pattern. Every neuron has a sort of, for example, let's say there is a neuron like this. This neuron may be something that is detecting this sort of a pattern inside, just this part of the 4, as its pattern. If it sees, for example, a 4 itself like this will have a very high value, like probably 0.9999 or something like that. If it says something like 3, it will probably have a very low value, 0.001 or something. The idea is a neuron normally tries to see if a pattern that it's trained to, like detect is present in an image or not. Two neurons now, obviously we understand what one neuron does, but so how does a neural network, the entire thing works? So what happens is we have a bunch of neurons that are connected to each other. For example, in this case, these two neurons, if you can see, they are trying to detect these patterns, all right? This, slanted diagonal, this straight, small line. They try to detect these patterns. Now, what we do is we want to, once we get one end of the pattern, we want that neuron to transmit its information to the other layers. That's how, other neurons as well. So what happens is that happens through this method. We have a thing called connection weight, which is used to weigh these neurons' values, and then they get transmitted to the other neurons. Pretty much, for example, this neuron is probably detecting the chance that whatever number I'm given is a 7. Now imagine this, if it's a 7 has both a top part, a top line like this, right? And a bottom slant, right? So what would happen is the way we would know if it's a 7 or not is if these two are both present in our photo. If they are, these two will both be activated. So this thing will only be high or will only get activated if these two are activated. That's why these connection weights are positive. What is this connection weight thing? Well, a connection weight is nothing but a way of weighing the features. For example, let's say you're trying to go for a housing price. You're trying to look for a house to rent. Let's say you have, 3-bedroom, 1-bathroom place. All right. You might think that's great. Now you see another house that has 4-bedroom, 1-bathroom, 5-bedroom, 1-bathroom. Right. Think about it. Normally, in your mind, how much do you think the rent would change between a 3-bedroom, 1-bathroom, 4-bedroom, 1-bathroom, 5-bedroom, 1-bathroom? It shouldn't change linearly. It shouldn't be like, okay, $50, $100 per month per room. No, because a 3-bedroom, 1-bathroom is one thing, but if I have 9-bedroom and 1-bathroom, that's not something where I would like to rent. Nobody would like to rent out. That's like a line in front of the bathroom of your own house every morning. So that's why we have weights. Weights kind of make sure that how much some particular neuron activation would have, should be given importance to. Now, look at the next part, the second, neuron right there. That neuron wants to see if there's a 1, if this photo has a 1 or not. Now, how do we have a 1? A 1 is normally, even if I actually do it like, sort of like a slant, like this, doesn't have any sort of straight line here, right? It only has this. That's why this neuron only gets activated when this neuron is activated and this neuron is not activated. That's why this connection weight is negative. Again, as I said, patterns. In everything a neuron does is seeing patterns. Now, basically, they are, as I said, neurons normally, this is how a neural network actually looks like. You have a bunch of neurons. Each neuron is connected to, the neighboring columns, or as we call it, layers of neurons. And basically, for example, every neuron is connected to all, there are different types of networks. The easiest one is called a fully connected or a dense network, where, as you can see, this neuron is, for example, all these three are actually dense layers, which means that every neuron in this layer is connected to every neuron of the next layer. This is connected to this one, this one, this one. So is this one connected to those two. This is also a dense layer. This is connected to, both of the neurons in the next layer, and so on and so forth. This is pretty much how, things get passed. So before we go into the next part, I'm going to show you one little thing, which is, again, in the main part, in the code. So we went up to this part, right? We saw that it's basically a bunch of, numbers between 0 and 255. Now, remember what I said, that a neuron normally holds value between 0 and 1, right? So we need to make those values from 255 to between 0 and 1. Now, one way of doing that is basically, this is what we call, it's a very, it's a term called normalization. All we need to think about right now is basically check the maximum value. In this case, the maximum value, this list can attain is 255. The minimum value this list can attain is 0. So what you do is you basically literally just do minimum value by maximum minus minimum. This is called normalization. If you don't understand it, don't worry about it. All it does is pretty much squish these 0 to 255 value into 0 and 1. That's it. That's all it does. So for example, in here, if I run this, it goes from, it basically, these two lines, what it does is it squishes these values from, the photo from having 0 to 255 to 0 to 1. So for example, now if you see the same thing, this particular, what was that? I equals 2, okay. It's the same one, right? It still looks like a 4, right? You can see this little thing that looks like a 4, but the values are, instead of big, gigantic numbers, they're, 0.5, 0.6, 0.8, and so on. Now, again, this thing also, it's the same thing. It's the same, number, basically. Now, here's the thing. If we understood how a neural network works, these things have patterns that goes on, and, gets pushed on. This is how a neural network looks like. This is the actual thing. Let's say you have a 5 by 5 photo of a 0. All right. What we do is we first try to flatten this image. How do you flatten it? Take all the pixels in this row, put them like this. Then take all the pixels of the next row and put it right next to it. This is called flattening an image. The reason we want to flatten an image is because normally dealing with a two-dimensional bunch of numbers isn't the best part to do, isn't really fun, let's say, for lack of a better word. So what we do is we basically try to flatten it by putting each of these rows one after the other. Imagine it to have like a Lego block, and you're putting every layer, next row of the Lego block right beside the other one, beside the previous one. Once it is done, what we do is we first have an input layer, this one. This has 25 neurons. Each of these blobs are neurons. There are 25 such neurons. And these neurons take each of these pixels. So for example, this neuron will take the first pixel. This neuron will take the second pixel. This neuron will take the third pixel value, and so on. Imagine these to be your eyes. This is pretty much, this functions literally like your eyes. They're the visual receptors of this neural network. They're like the rod and cone cells. These then go into like push their information into these things called the hidden layers. The hidden layers are the ones that, basically does the brain, like functions as the brain. They're the ones that tries to find patterns. This one, for example, this is connected to all of these 25 neurons. This will try to find a particular kind of pattern of, something here. We don't know what that something is. All we know is that something is going to definitely help this neural network to identify one or two types of digits. Then at the end of which we have something called the output layer. So normally, when you consider digits, how many digits are there in total?
In what?
In total, how many digits are there?
0 to 10.
10, yeah, exactly, 0 to 10, right? Or rather 0 to 9. So there are 10 digits. That means what we do is we use this output layer that has 10 neurons. Each neuron corresponds to a digit. If this is a 0, ideally, this neuron that corresponds to a 0 will light up. All the other neurons would ideally stay dark. More realistically, what happens is they also get like a little, activated, but not as activated as this one. Similarly, if we see a 6, this neuron gets, lit. Everything else just stay dark, and so on. Now, obviously, let's go back to the code again and see how to flatten an image. So this is how, things in the X-train looks like. It's still a 4, right? It still looks like a 2-dimensional image. What we do is, X-train still is a 28 by 28 image here right now. So, and this is where Numpy comes in super handy. So how you can use to do like flattening of things in Numpy is literally this, numpy.reshape. What reshape does is basically takes this -1 means don't worry about that dimension. Just make sure that the next 1 or 2 dimensions are this. Like for example, this means I don't care what number you get on that part. All I need to do is make sure instead of these being 28 by 28, I want them to be a flat 784 vector. Because 28 into 28 is 784. Yeah, 28 by 28, 784. So this is how that thing works. Like that -1 that helps in basically, again, this is also another cool part of Numpy. If you don't want to put anything here, you want to see like however many number, it comes up, don't worry about it. I just want to flatten these 2 dimensions. You do it like this. You can like literally say -1, which means I don't care about what number comes out in this dimension. I just want these 28 by 28 image to get flattened like this. So if you, for example, put that in, you'll see it basically becomes, now it's like 784, So what we did here was we put to this, flattened it, just like we saw here, right here. We just flattened it. Now after that, we have a Y train. So X train has the images. These are like the questions. Y train has the answer key. But this, if this is I equals 2, so X train, 2 is this image. Y train 2 is probably 4. For example, let's actually check it, right? Y train 2 is going to be 4. You see? Now, here's again, these are things which are implementation, level, is this thing called two categorical. So for example, normally we do definitely try to, make it like, try to put out like one number. We're trying to learn a digit, and a digit can be represented by one number. But because we're talking about neural networks, it's easier to represent them as vectors. What's a vector? It's just a list of numbers. A vector is nothing but it looks pretty much like this. All right, 0, 1, 3, 5, 6. This could be considered as a vector. If you don't know what, if you don't know what a vector is, just remember them as a list of numbers. Not unlike the one we're getting at the end of this. This is basically what this is going to give me as a list of 10 numbers. The first number will represent how if there's a possibility of a 0 or not. Second number will represent if there's a possibility of 1 or not, and so on. Similarly, because it's far easier or faster to do these sort of calculations, what we do is instead of using, instead of trying to use, instead of trying to use these sort of, just like numbers, what we do is we try to change them or vectorize them. For example, this is that particular thing. Keras.utils, two categorical. You put however number of actual, classes or types of object there are. In this case, as we know, for digits, you only can have 10 digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, pretty much. So you basically say, okay, vectorize them so that instead of having one number, I want just a vector, and that vector should tell me what the value is. For example, in this case, this would give me this. This is 4, right? Vectorized form of this would be this, this is what we call as one-hot encoding. 0, 1, 2, 3, 4. 4 is the only one with a 1. Everything else becomes a 0. The reason why we do this is because it's faster to process this using, when training or any kind of deep learning task. It's easier to process vectors with vectors as opposed to, converting every, single iteration, converting whatever you have here to vector, and then, whatever you have here to vector and trying to, do stuff with it. A second reason is, ideally, let's say if it were a 4, I want this one to be as bright as possible and everything else to be as dark as possible. The one way I can do that is if I keep it as a vector, as a list of numbers, as a vector, and just try to push, try to get certain part of how much the others are, lit up as an error metric. Now, we've been talking about these hidden layers, like these brains. What kind of pattern do they see? This is what they kind of see. Normally, a hidden layer, they kind of detect underlying patterns, as we already said. For example, in this one, in this one, as you can see, there are two hidden layers. This would probably detect certain simple patterns. For example, something like this. These straight lines, small lines, a little curved line, diagonal, straight line, on the top, straight line on the bottom, things like these. These are what this layer would try to detect. Each of these neurons will detect a different pattern, but the idea would be pretty much the same. It would have a very similar, level of complexity. The second layer in that would try to probably determine something if these are present. this sort of thing. Each neuron will do something different, but they'll try to check something of, if there's a circle or not, if there is a half circle or not, and things like that. Now, this is where the deep learning becomes kind of like an art more than a science. The more of these hidden layers you put, the more complex pattern it can detect. Yes. But too many deep learning, too many hidden layers, and what happens is that network brain starts seeing patterns where there is not really a pattern. Imagine something like this. Nobody here writes for like, this, like this, right? We always go for something like this or, this. We want a neural network to understand that this is a 4, this is a 4, this is a 4. However, if you give too many, deep, like, hidden layers, what happens is it sees this thing, this little downward slope. It gets fixated on that and gives you the wrong result. Pretty much as much like, a conspiracy theorist's brain, pretty much. It basically becomes something like that. But yeah, like that's pretty much how it becomes. Like, for example, this is a 4, right? Have a proper number of layers, it will detect properly. Have a little bit more, and it will try to see, oh, there's a little loop here. You see how these pixels are like, going like this? There we go. The entire thing will give you some completely different result than what you expect. So, for example, now let's see. What else? Now, the last part that I wanted to tell you guys is something called activation functions. As of now, we have seen how a neuron, what neuron connections mean. That they are pretty much, these neuron connections sort of help a bunch of one layer of neurons to pass information to another layer of neurons and make the next layer try to detect something more deeper, some more, complex patterns, things like that. For example, these two neurons, they're detecting these, these straight lines. This neuron will try to detect if this is there and this is there, if both these two, pattern is present in our image, and so on and so on. However, there are certain times that we want to do something called, try to work on something called activation. So an activation function is sort of like a tool that we can use to regulate that number or the value of a neuron, and secondly, try to make it detect more complex patterns. For example, there is one activation function called rectified linear unit. What it does is it tries to detect, it tries to see this number. If this number is greater than 0, fine. I don't, it doesn't do anything with it. However, if that number is less than 0, it clamps it to 0. It says, okay, if it's negative, just put it as 0. For example, in this case, the reason this is done is so that, again, one is this introduces something called non-linearity. And that's important because normally we don't normally see linear patterns, in nature. Again, remember, let me, for example, let's just talk about the whole housing crisis thing. If you're looking at a place which is 3-bedroom, 1 bathroom, you can, even in those two, like just 3-bedroom and 1 bathroom, you will find huge number of variations that are completely not linear. It could be because there is a dependency on, the area where you're, where the house is located. If it's located somewhere near, I don't know, the outskirts of the city, it should be dirt cheap. If it is located like literally next door to, I think, the Ruby Diamond Theater, it's going to be sky high. Those sort of things, and these sort of, changes happen non-linearly, right? Because again, there are, another example is human face, detection of human face. Face detection, something, how you guys all use Snapchat, right? Snapchat uses, face detection. It's funnily enough, that face detector is known as YOLO. I'm not even joking. That's the name of that, of this neural network. It's called YOLO. And the thing is, it also has a lot of, when you're trying to see someone's face, you look at them and you realize that there's a lot of things that are like not linear. For example, you're looking at a lot of things. You're looking at 2 ears right here, 2 eyes here. These eyes can actually change a little bit in position, depending on, the facial structure. You have a nose. The nose can be like this, it could be a little bit crooked as well. You have lips, which are also, all is they're probably just beneath the nose. But other than that, different people have different lips, different color of lips, depending on how many times these person has spoken on whatnot, or if they've put lipstick. Things like these, there are a lot of, non-linear things, present in trying to detect patterns, especially patterns that are very simple, that takes easy, that for us, it's easy to detect. For those things, what we do is we use these things called activation functions. This thing helps us detect more complex patterns. ReLU, for example, does. Another kind of activation function is called softmax. So before we go for softmax, let me show you something. Remember how I said this layer is going to be the output there, where if I see a 0, this neuron becomes very bright, this neuron becomes other neurons become very dark. Here's the thing, we kind of want to do something better with that. We don't want just numbers. Like, for example, in this case, if this is my output layer, this one probably detects a 7, this one detects a 1. I don't know what these numbers would mean. There could be some other, neuron that's probably 25 or something like that. It doesn't make any sense. To make it, to make it more like a probability value, what we do is we take these and pass it through this thing called softmax activation, which gives us probability value. A probability value means that this entire, like this layer of the output layer, if you take all of these neurons values, you get 1, basically, they sum up to 1. In this case, for example, from this 1.0 minus 0.28, what happens is we get these 2 values. That means there's an 80% chance this image is 107. Why? Because I see these 2. There's a 20% chance this image is 101. Because again, I see both of these and I don't think it's, one has something on top, but who knows, That's what happens when it comes to, that's how like activation functions work. So now that we know that, let's begin our, our model. This is pretty much our sequential, so in order to get a model, in order to make a model in Keras, what you need to do is you need to first call this one. It's called Keras sequential. A sequential model means that, so there are various kind of models in deep learning. One type of model is called sequential, which is pretty much what I showed you guys a few minutes ago, where what happens is let's say you have a layer like this, some stuff comes in, let's say an image or whatever. The output of this then goes to the next layer. The output of that goes to the next layer, and so on, so on, so on. Pretty much this is how a sequential model is considered. Again, let's say we are doing the same thing as we were doing in this particular slide, right? This particular slide, all right? So what happens is we're going to first have 784 input, neurons. Each neuron corresponds to each pixel. Then we have each of these basically. So the way we do it is keras.layers.input. This basically means it's the input layer. Then we have something called the dense layer. A dense layer is nothing but, as I said, every neuron is connected to every other neuron, on the previous layer pretty much. We had what, 16 of these here? So we will have 16. Activation, ReLU, which is like that entire thing, clipping the negative values down to 0, positive values, you can do whatever you want. Another layer we add. So model.add basically adds these layers, like basically you have this one layer, the input layer, then the dense layer. You basically model.add adds these layers. Again, you can use, these are all Keras like has them. And you can also make your custom layers as well, but Keras normally has them. So activation, you give ReLU. You can also give a name to your, layers as well if you want to. And the final layer is softmax. It's a dense layer. Final layer is my output layer. 10 digits, therefore 10 here. And the activation is softmax. You can also run a pretty handy, model.summary. Now we have this thing, which is, if you remember the loss function and optimizer. Normally, a loss function is something that pretty much works as a way of telling us, is this how bad or good is this computer doing its work? An optimizer is like a teacher. It tries to make sure that anything that is, pretty much given a loss, how bad, when the model is performing, the optimizer tries to tune these weights. Remember when at the beginning I said that the optimizer, it tries to be like a teacher, it tries to fine tune the network. Well, what does it fine tune? These weights. These connection weights. After seeing this, for example, the optimizer, the loss function will have not a complete 0 value. It will say, yes, this is a 7, and he did correctly predict it as 7, but there's a 20% chance that he thought this was a 1. So the loss function is not going to be 0, it's going to be something above that. The optimizer is going to take that and say, okay, you need to make this one smaller. So these weights, these two weights are going to change. This one needs to be higher. These two weights needs to be changed. Again, this entire thing happens in, a loop. This loop. Remember this loop? The neural network gives its predictions. The predictions then goes through, how good did the model do or how bad did the model do? The loss function. That loss function goes to the optimizer, who tries to, change the weights, fine tune. Now you see the fine tuning thing? It's just changing these weights of the neural network to make it do better predictions. This entire thing happens in sort of like a circle, a loop, this entire thing. One of these loops are called epochs. Normally, we run this for 15, 20, 30, 100 epochs, depending on the situation. But each epoch is basically a loop where all of these training data are taken, pushed through the network, the loss is computed, and the optimizer fine-tunes the network for every single image in the training data. That entire thing is called one epoch. Now, let's go back to the code. This is our model. This is our neural network. What we need now is to define this error and this optimizer. That's what we do here. Compilation. Loss is categorical cross entropy. Don't worry about it if you don't understand it. It's pretty much a function that we use to calculate how bad or good the model is doing. For example, let's say if you're trying to go for housing prices, what you do is you show a house to, let's say, the model. This is how a more loss works, basically. And it gives, rent prediction, right? You see the actual rent of that house. And a loss here would probably be something like this. Rent prediction minus actual rent whole square, something like this, So categorical cross entropy is something of that sort, where it is a loss function that tries to see how good or bad the model is doing in classifying handwritten digits. The optimizer is called Adam. The optimizer normally is like a teacher. It basically tries to make this model understand what weights to tune, right? So Adam is sort of like one of the best teachers out there. That's all I can say. If I want to go any further, there's a way too much math to, even cover right now. So now what we do is we compile, and before training, let's see how the model performs, all right? That's just terrible. Like out of 5 out of 100 handwritten digits, can it actually say as, oh yeah, this is correct, this is 7 or 8. For example, and this is how, you remember that little thing what we're calling about, how the weights look in a neural network? This is what pattern the first layers, 6th neuron of the first layer is detecting right now. Literally nothing. Same with the 7th layer, second layer, this is what's happening in the second layer. Nothing. Like, do you see any pattern here? There's literally no pattern. There's literally nothing you can detect. Like, what is it? Like, it's kind of random. It literally looks like, what happens when your TV goes to static. I just want to check something. Okay, wait. Yeah. This is how bad it is, where when we're trying to predict, let's say a 7, when we are making the model predict a 7, it's predicting it as a 1. That's how bad it is right now. Now we start our training. This is the training. Each of these epoch is one such loop over the 60,000, training images that we have. Now, after this is done, let's now evaluate this model again. From 5%, like out of 100, in managing to probably classify, correctly identify 5 digits, it goes to 95%. 100 images, this is going to classify 95 of those images, digits on those images correctly. Just what, 15 epochs, that's what it did. Now, if you look at these weights, check it out. Doesn't this look like it's trying to, detect something like this? It tries to detect something that looks kind of like a 6 or a, or even maybe a 5, right? Something of this sort. Compared to a random, pattern, now our neural network is actually trying to determine or understand or find a pattern that may actually be present. This is what training does. This is the beauty of training. This, for example, is also trying to find, you see, check this out. This is the second layer, right? This is the second layer's thing. Doesn't that look like a 5 to you guys? That's what happens. That exact neuron before training was this. In reality, what happened is something like this. This is exactly how, neural networks worked. This is what was going on throughout those training. As you can see, when we were doing the training here, this one, as each of them, did like a slider bar thing, this was what was going on behind the scenes. At first, the network tried to, identify these photos. Network doesn't know shit. So it identifies everything as 0. Loss value becomes very high. It's literally out of 6, you manage to incorrectly predict every 6. Optimizer takes that loss, goes back to the neural network, tries to change these weights. Then comes the second epoch. See, the model's weights change a little bit. Again, pass it through the network. One of those 4 images it managed to predict as a 2. 1. High, definitely very high, but not as high as before. Before it was like pretty much like, what is going on? And now it's like, okay, this thing manages to know how a 2 looks, maybe. Optimizer again takes that, sees, okay, this is where you need to change your weights to make a better prediction. Second time, 2 out of 6, 1 more than the previous one. Again, optimizer again takes that, pushes it, tries to see what needs to be changed more. This time it's 4 out of 6. Majority of the predictions are correct, but there's still room for improvement. The loss is low, but it's not 0. Finally, the loss becomes 0 because all 6 out of 6 are correct. This is essentially how a neural network works. And I think I am done. Any questions by any chance? Anyone? Yeah.
Yeah, the optimizer, would that be something that is continuously using within AI?
Yeah. Every single epoch, after we get the loss, like how bad or good the model is doing, the optimizer takes that loss every single time and tries to push for a better model, like kind of tune the connection weights. Yes.
So this is all about building the model, but there is some point where you stop and you use the model, right? You don't use the optimizer with the error.
Yes. So okay, so that's a good question. So what happens is, this is how the model is built and trained. And then what we do is we finally deploy it for production, which happens when, let's say, you see this test, this test accuracy, right? 95%. You do a bunch of these, validation tests, trying to see more deeper. Like, for example, instead of just doing this, you try to do something called the confusion matrix. We try to see that I don't care about how many it gets right, rather what kind of numbers it gets mixed up and so and so. And after a lot of those work, what you do is you finally, if you're talking about like corporate deployment, like it's like Amazon, Snapchat, that's what they do, is after clearing a bunch of these tests or exams, they finally deploy it. And in deployment, what happens is it doesn't do the backward pass. It just, like, for example, where is it? So it doesn't do a backward pass. It just goes like this. Like, it takes an image, it just goes to this and gives you the prediction. That's it. We don't need loss or optimizer there. That is true. Sorry, I forgot to mention that. Yes.
So is the curve, like the learning curve for like percentage correct the number of epochs that it's gone through? Is that like logarithmic? Will it ever reach 100%, or does it take like an infinite number to get to like 99999?
That's a good question. And let me introduce to the concept of overfitting, aka making a neural network think like a conspiracy theorist right now. So you see, let's say every epoch you see the training loss, which is the loss from the training set, and you also try to get the loss from the unknown or the validation of this test set as well. You can actually do that. So let's say I do something like that. What happens is loss value, and let's say this is epochs. The training loss does decrease like this. However, the validation loss decreases. This is, by the way, the training loss. So training data loss, basically. The validation loss, it decreases to a point and then increases. And believe me, I'm not trying to exaggerate this, but this is what happens. For example, take a closer look at, this one. Where is it? Closer look at this. This is the training loss. So in the training little, the training data, it had 96%, accuracy. Look at the test data, 95. So it's already starting to go towards this point. If you make more layers, if you try to do this for a long time, you might actually start getting like here. With MNIST, it doesn't happen often, but for example, the project I'm right now doing is age detection. It's like trying to figure out someone's age given their face. And yeah, like it overfits a lot. Like it like tells pretty much like things like unknown faces. Let's say I show you some unknown face and it pretty much says, oh, this guy's 100 years old, may not be even 30, but it just like, like that sort of thing happens.
Thank you so much.
Thank you so much. Thank you, everyone.
Thank you guys for coming. I hope you guys learned a lot. I know we already gave a round of applause already, but thank you, Adi.
Thank you so much.